Kind of hit the ground running this morning, huh? Do we have any more questions from the homework? Oh, I turned on the recorder and now nobody has anything to say. Okay. Well, the sign-in sheet's going around, so everybody make sure you sign it. Oh, it's come around, so has everyone signed it? So seriously, how's everybody doing with the homework so far? Okay. Here, got someone else needs to sign in. Just here, we'll pass it back to you. Sure.
Okay, because this is, I don't mean to keep bringing this up, but I'm getting confused on this. So you said that if this is negative, then it changes the direction.
Right.
Starts down. But what if this is positive? I thought this is the amplitude is what changed the direction. See, on this one, so since it's just 2 pi.
Okay.
It's -4 drop down to 4.
I understand. Okay, I understand your question. Let's look at that because that's actually a very, very good question. This is something that will be confusing if you don't think about it. What is the difference between -4 sine x, or let's say -4 sine 2x and 4 times sine of -2x? Well, the first difference is here we have a negative amplitude and a positive omega. Here we have a positive amplitude and a negative omega. But remember that the sine function is an odd function. Does anyone remember what that means? Who can tell me what it means to say that a function is odd or even? A function is odd if sine of negative x equals negative sine of x. Because the sine of the negative value of x is equal to a negative of the sine of the positive value of x. Because sine is an odd function, both of these expressions equal the same thing. They're equal. Okay? Cosine, on the other hand, is an even function. So if you change the sine of omega, of the angular frequency, of the value that you're taking the cosine of, it doesn't change anything. It's still going to be the positive value. However, in the case of an even function like cosine, changing the sign of the amplitude does change things. Now, back to your question. In the case of the sine function, both have the same exact effect. If you're taking the sine, 4 times the sine of negative x, that's exactly the same thing as taking -4 times the sine of x. So the effect would be the same. In either case, it changes sine from doing this, in the case of 4 times, in case of the positive angular frequency, or positive omega, to doing this in the case of the negative angular frequency. Changing the sign of the amplitude does the same thing, because now you take the sine of x, which here would be 1, but you multiply it by negative, and that brings it down here. Okay? With cosine, you start off with a cosine of x. Well, at 0, it's 1, so it starts off at here. And then it goes negative. If you take the cosine of negative 1, it still starts off in the same place and does this. So, but if you change the sign of the amplitude, then the cosine of 0 is still 1, but multiplying it by a negative number brings it down here. And you basically shift the phase. It's like shifting the whole thing left or right by what? Pi over 2 degrees? Pi over 2? Maybe it's pi. Say again? Well, this would be pi over 2, yeah. So you're not shifting it pi over 2, you're shifting it pi. You're shifting it a whole half of a cycle. But the point is, doesn't matter. We could work that out if we needed to. But the point is that changing the amplitude of an even function will shift it left and right. Changing the angular frequency will not. But for an odd function like sine, changing the sign of either the angular frequency, omega, or the amplitude is going to have that same effect. It's going to shift it left and right. Now, does that make sense? Is this clicking with everyone? Are you still? Okay. This was just another one of a myriad of little tiny details that you need to keep sorted and keep straight in your mind. But really, maybe hard to believe right now, but once you do get all of this sorted, and it does start to click, it really does get just dirt simple. Are there any more questions from any of the homework? Well, I'm going to take the silence as a resounding no. And we can start on section 2.5. And today we're going to look at graphing the functions of tangent and cotangent and secant and cosecant. Can everyone see over here? Okay. I want to try and keep one graph showing everything, if I can. Now, we've already looked at graphing sine and cosine. The sine function does this. And the cosine function does this. And everybody take a picture, because that may be the prettiest sine and cosine function I've ever drawn. But you'll notice how they're shifted. They're shifted pi over 2 from each other, 90 degrees. And now we're going to look at graphing the tangent. Yeah, let's graph the tangent. Looking at this graph, who can tell me what is the definition of tangent? Y over x, or sine over cosine. Well, here at 0 at the origin, what is sine and what is cosine? At 0, at x equals 0, what is sine? Sine is 0, cosine is 1. So tangent at 0 would be 0 divided by 1 is 0. Now, everybody try to think back a few weeks or lessons. Who can remember what the domain? Remember the domain and range of these functions? Well, the range of sine and cosine was limited to an interval of 1 to negative 1. What's the range of tangent? Minus infinity to plus infinity. All real numbers. But what's the domain? No, not quite. Good guess, though. When sine, it's all real numbers except when sine equals 0, which happens at multiples of pi. Sine is 0 at 0 pi, at 1 pi, at 2 pi. So the domain is all real numbers except multiples of pi. So here, for example, we know that this is not part of the domain of tangent. We know that the y-axis is not part of the domain. X equals pi is not part of the domain. X equals 2 pi. And I'm taking time to put in all these little dashed lines or dotted lines for a reason. Those are called asymptotes. They are points on the x-axis, vertical lines on the axis that the value of tangent can get arbitrarily close to, but never touch, can never equal it. Now, as long as you don't get quite to zero, you can get as close to zero as you can arbitrarily imagine and have a well-defined value for tangent. But you can't get to zero. So they're called asymptotes. And we know right here, the value of tangent is zero at the origin. What is the value of tangent at pi over 2? We did that backwards, didn't we? Tangent is not, it's not cosine divided by sine, it's sine divided by cosine, which means this is all wrong. These asymptotes are for, well, we'll use them in a little while when we do cotangent. Right now, we're looking at the tangent function, and it becomes undefined not when sine is 0, but when cosine is 0. So the domain of tangent is all real numbers except odd multiples of pi over 2. At 1 pi over 2, or at 3 pi over 2, minus pi over 2, minus 3 pi over 2. All real numbers except multiples of pi over 2 where k is an odd number. So it's undefined at odd multiples of pi over 2. Now, that means at pi over 2, we don't know what tangent is. It does not have a value at pi over 2. But what if we were just a little bit before we got to pi over 2? Then it would be sine, which is very nearly 1, divided by cosine getting smaller and smaller and smaller, which means the smaller cosine gets, the closer to the asymptote it gets, and the higher, the closer to infinity it gets. What about at pi over 4? What's sine and cosine at pi over 4? Is it square root of 2 over 2, or 1 over the square root of 2? Point is, at 45 degrees, at pi over 4, sine and cosine are the same thing. They're equal. So when you divide either by the other, what do you get? Unity. You get 1. So there's the tangent function coming in from the right, or leaving the origin and going towards pi over 2. You go through the same exercise. And you find the tangent function doing that as you move left of origin. You're still dividing sine by cosine, but what did we talk about at the beginning of the hour? Sine is an odd function, cosine is an even function. So the sine of negative x is negative the sine of x, but the cosine of negative x is still the positive of x, or still the positive value. Which means here you're dividing a negative by a positive. So you get the same values, but they're going in the negative direction. What if you were just a little beyond pi over 2? If you say you're at 95 degrees. Now you've crossed over into quadrant 2. Once you get into this region here, now sine is still positive, but cosine becomes negative. So if you're just a little bit beyond pi over 2, cosine is still an incredibly tiny number, just not quite 0, but now it's negative. And sine is still positive. So once you get just a little past pi over 2, what happens to the tangent function? It's going more and more and more and more and more positive. The instant you cross that asymptote, boom, it becomes very nearly minus infinity. It becomes strongly negative. And at 3 pi over 4, it's negative 1. And at pi, sine is 0 again, so tangent goes back to 0. And it repeats this pattern. You do the same exercise here. You get this repeating pattern for the function of tangent. Now, I'm going to give you a little tip here, because you've already what some of you have already learned, hopefully, is that your calculator will quickly get you into trouble when you're doing trig. We learned that the first time you learned this was remembering to switch from degrees to radians with your calculator. There's a homework problem from a couple weeks ago where it was asking for the sine. You use your calculator to find the sine and cosine of like pi over 3 or whatever. I don't remember what it was, but the first answer was like 0.32. Unless you forgot to put your calculator in radian mode. And if you left it in degrees and you just divided pi by whatever and punched the sine button, then it gave you an answer of 0.01. So, your calculators will get you in trouble doing trigonometry if you're not careful. Here's another time when this can happen. The definition of a function, if you recall from algebra, is that for every value of x, you can only get one and only one unique value of y. And that's true. No matter where you go on x, you're going to get one and only one value of y. But if you remember solving the quadratic formula, for every value of y, you can often find more than one value of x. The same is true here. You pick any value of y and you're going to get an infinite number of x values that will solve for that x. Is the algorithm in your calculator going to give you an infinite number of solutions when you take the inverse tangent of a number? You plug in a value and say, what angle is this, or what x is this? It's going to give you an answer right here between pi over 2 and minus pi over 2. Now, that's all well and good unless you happen to be at 95 degrees. And if you're at 95 degrees, which would be right here, just past pi over 2, then your tangent function is going to be some large negative number, and when you plug in that large negative number and hit inverse tangent, the calculator is going to say, oh, you're right over here, just shy of negative pi over 2. So instead of 95 degrees, it's going to give you minus 85 degrees. This is one of the things you have to sort out in your own head before you trust your calculator to just blindly give you a number. So, just a tip. You will also discover the same thing is true with the other functions, cosine and sine. The algorithm is only going to give you the first value it gets to. Depending on the algorithm, I think cosine is going to give you something between 0 and pi, and sine is going to give you something between minus pi over 2 and pi over 2, but you'll have to play around with your own calculators to see how they work. But this is something that you need to be aware of if you're trying to actually use any of this trig to solve a real problem. We got pages sticking together? I sure do. Now let's look at the cotangent function. Told you those other asymptotes were going to come in handy. Cotangent is the reciprocal of tangent. So, what does that mean the value of cotangent is at pi? At 0. If tangent is 0, the reciprocal of tangent is 1 over 0, which is undefined, which means the y-axis is the first of those asymptotes for the cotangent function. Who wants to tell me what's the domain of the cotangent function? Obviously, the range is still all real numbers minus infinity to plus infinity. But the domain changes to the one we first worked out when we were doing it backwards at the beginning. It's undefined at all multiples of pi. These are the asymptotes for the cotangent function. So where is the first time that the cotangent function is going to be 0? If cotangent is the reciprocal of tangent, that means instead of sine over cosine, it's cosine divided by sine. So when is cosine 0? At all odd multiples of pi over 2. So the cotangent function becomes 0 at every point where the tangent function is undefined. So at every asymptote of the tangent function, the cotangent function is 0. Now, what is the value of the cotangent function just on the plus side of pi over 2? just right in here. What is cosine? Slightly negative. Still very near zero, but it's just slightly negative. Sine is pretty close to 1. So it's a positive 1 divided by a very, very slightly negative, not quite 0. So it's going to be a negative value. And it's going to be very nearly, am I right? No, I'm doing this backwards again. Cosine it's cosine over sine, not sine over cosine. So it's a very, very nearly negative. It's just barely negative, but it's very nearly 0. But it's just this side of 0. And at here right here where tangent is at -1, what's the cotangent? It's the reciprocal of -1, which is still -1. It's 1 over -1. That means right here, the cotangent becomes -1, and then it approaches this asymptote at -infinity. Same here. And what you can do is go along here, and at everywhere that the tangent is 1, the cotangent is also 1. And there's the graph of your cotangent. Do you have any questions? Well, what is not clicking? What's not making sense to any of you yet? Well, and I do want to take a moment and point out to you that the same thing that I warned you about with tangent is going to be true with cotangent. Your calculator will get you in trouble. You have to figure out which one of these curves you're looking at when you start solving for a value of x. You give it any value of x, it'll give you one and only one unique value of y. But for every value of y, it will give you an infinite number of values of x that will provide a solution. And you have to pick out which one of those infinite number of x values you're looking for. Did I point out to y'all yet that once you've finished the course in trigonometry and you go on to whatever your chosen field is and you start having to actually use trigonometry to figure out how big of a radius you need to put in the conduit, or how long the tube can be before you plug it into the patient's arm. Obviously every one of you in here has a reason for learning trigonometry, or they wouldn't require you to learn it. You're going to use it in whatever your chosen field is. If you're feeling a little bit frustrated or overwhelmed or confused with all of this, with all of these 6 functions, let me tell you now that you will probably go the rest of your life and never once think about a cotangent function. Okay, they just don't come up. In real life, you're going to use sine and you're going to use cosine, and maybe if you are unfortunate enough to work in electrical or electronics, you might have to use the tangent. And basically, anytime you have to start sussing vectors, you start having to figure out vectors, you're probably going to use the tangent some too, and it will get you in trouble for this very reason. But take heart. All you need to learn this stuff for is to get through this course. And believe it or not, you get all of this stuff sorted in your mind, and all of it is going to start clicking. Most of you probably don't realize this yet, but when it comes to learning mathematics, you're over the hump. You're on the backside of the learning curve now. You are beyond the hump. The hump was algebra. Once you got past algebra, you're on the downhill side. Now, it's at this point, it's still very shallowly, very slightly downhill, but it is a little bit downhill from algebra. And if any of you go on to do calculus, you're going to find that it's actually even a little more downhill. And believe it or not, if you get all the way up into differential equations and vector calculus and that sort of thing, it gets even easier and easier the further you go. If you get all of this sorted now. So, I'm not telling you this to tell you that you can then just forget about trying to figure all this out. I'm telling you this to try and reassure you there is a reason you need to figure all of this out. Okay? The good news is you only have to do it once. You figure it out, get your mind wrapped around this stuff now, and it's going to carry you like a sail full of wind from now on. You don't wrap your mind around this now, and it's going to drag behind you like an anchor for the rest of your career. I don't mean to frighten you. I'm trying to encourage you. Hopefully I'm not doing a horrible job of it, but you really do work this out in your mind. You can read the book too. Everybody here is literate. The book will help you sort some of this out as well. And hopefully, if you ask questions, hopefully I can help you figure out some of the stuff that does confuse you. But I really, really need y'all to ask questions in order for me to try and explain it better. Okay? So, everybody clear on tangent and cotangent? Get this image in your mind. Notice how tangents are all going up and to the right. Cotangents are going down and to the right. Or up and to the left. Or if you're, what was that guy's name? Did the Kennedy assassination movie? Kevin Costner. Back and to the left. Back and to the left. Back and to... Does anybody get the reference? Okay. You have no idea. The movie is called JFK. It's a really fun movie to watch. Do not take it seriously. Okay? All right, well, then let's move on to secant and cosecant, because, I don't know, I left my watch at home. Can someone read that clock? Yeah. Okay, well, the onus is on y'all to let me know when we're out of time, which means you need to let me know before we run out of time, because sometimes it takes me a while to stop. I'm old and my brakes don't work so good. Let's look at cotangent. Go ahead.
That green line over there is that sign?
Nope. Green line is 1 at 0. Which one is 1 at 0? Cosine. Sine is 0 at 0. Sine is red. Cosine is green. And we're about to use them. Because now we're going to look at graphs of secant and cosecant. Make sure everybody over there on that side of the room can still see over here. Y'all better not be planning a pizza party without me.
We make it through this class, we'll have a pizza party.
Well, I'm fat enough, but I appreciate the thought.
Okay.
How about I just try to get you through this class regardless? Okay. Which one was cosine? Green? Wait, what does the book do first? Does the book do secant or cosecant first? They do both of them together. Okay, great. Okay, let's put in our cosine function. And now let's put in our sine function. Well, I'm really getting good at this, aren't I? Shut up. That's our sines and that's our sine and cosine. What is the definition of secant? Reciprocal of cosine. There it is. And cosecant one over sine. And if you're paying attention, you'll notice I kept the colors coordinated for you. You're welcome. Okay, well, let's start with secant. What's the range of secant? Oh, getting tricky here. It's not quite. So we'll come back to range in a minute. It's going to become visually, intuitively obvious in just a little. Say again? Or less than -1. But that's going to become visually intuitive, obvious in just a little bit. Let's talk about what is its domain? Where is secant undefined? What are these called? Asymptotes. Very good. The domain of cosecant, the domain of secant, all real numbers, that funny R with the double lines, if you're not familiar with it, it actually looks like this. And some books put little curly cues on it to make it look even prettier. That's a standard symbol for the set of all real numbers. So, the domain of secant is all real numbers except odd multiples of pi over 2. This vertical line is shorthand for such that. And it's part of set notation. What this says is k pi over 2 for all k equal odd numbers. So, secant is undefined everywhere at all odd multiples of pi over 2, or in other words, everywhere that cosine is 0, because secant is 1 over cosine, and 1 over 0 is undefined. So let's look instead, where's the easiest place to find the exact value? Everywhere that cosine is equal to 1, what's the value of secant? 1, exactly. 1 over 1 is still 1. So everywhere cosine is 1, secant is also 1. What about when cosine is negative 1? Secant is negative 1. Now, what is it? What is secant when cosine is just a little bit less than 1? The reciprocal is going to be just a little bit more than 1. And when it's 0, it's way off the board here. Same thing happens here. When it's a little bit less than 1, when cosine is a little bit less than 1, secant is a little bit more than 1. The closer it gets to 0, the closer secant goes to infinity. Same there. What about when it's negative 1? Just a little bit less than negative 1. When cosine is a little less than negative 1, secant is a little more than less than negative 1, and if that confused you, good, it should. It doesn't make sense in English, but in math it works out. It does this. And that is why I tell people I'm a physicist. I can't teach you how to pronounce my name without drawing pictures. We get the same effect over here. And now, just to keep the color coordination from being confusing, let's get rid of the cosine. And there's your value of secant. Now, does it make sense when we say that the range of secant is all real numbers? Well, you know what? Instead of writing it that way, let's write it this way. The magnitude of x is greater than or equal to 1. I guess I should say y. If y is greater than 1, then it's greater than or equal to 1, then it's in the range of secant. if y is -1 or less, then what's the magnitude? The principal square root of the square of the number. -1.1 times -1.1 is positive 1.1 squared, and if you take the square root of it, you get positive 1.1. The magnitude of y must be greater than or equal to 1. That's the range of secant. How much time we have left? And we go to 9:30 or 9:25, right? So we got another half hour. Okay, we're doing good. Who wants to take a guess at how this is going to go for the cosecant function? We find all of the points where sine is 1 or -1, and that gives us the value of cosecant at those points. If we look at all the places where sine is 0, we get all the places where cosecant is undefined. And for the record, there is absolutely nothing in the world wrong with understanding these things visually, with looking at the picture and seeing what it looks like, so that whenever you are thinking about it and staring at your calculator, instead of just seeing some numbers, you can actually have a mental image of what it is you're dealing with. What's the period of our tangent function? What's the period of sine and cosine? Two pi. Say again? No, that's the period of a function of sine of omega t or omega x. Then the period becomes 2 pi over omega for that function, for that particular expression. But in the general case, the period of sine and cosine is 2 pi in both cases. What's the period of tangent? Just look at the picture. Look at the picture and see what is the period of the tangent function. It's still pi. Even though it's undefined at pi, you can get arbitrarily close to pi. Not pi, pi over 2. To any of the asymptotes, you can get arbitrarily close. So at what point does it how long does it take to get from this point on pi to the next time it gets to that point on pi? I'm sorry, not tangent. From -1 to the next time it's -1. Well, how long does it take from the first time it's 1 to the next time it's 1? The period of tangent is pi, not 2 pi. It's half the period of sine and cosine. The same thing is true of cotangent. The period of cotangent is also pi. Say again? The period of both tangent and cotangent is pi. And that really makes sense if you figure that cotangent is just the reciprocal of tangent. So whatever the period of tangent is, it's going to pretty much have to have the same period to be, when you take the reciprocal. Now, this one is kind of hard to wrap your mind around when you look at it. What's the period of one of these monstrosities? It is, but why? That's a good answer. That is actually a very good answer. If it's the reciprocal of a function that has a period of 2 pi, it pretty much has to have a period of 2 pi. But look at the picture. Visually look at what's going on. That does not intuitively leap out at anyone and say, oh, look, there's a periodic function with a period of 2 pi. It looks like a bunch of isolated mountain peaks. Not one continuous function. But, and this is the point, it's not continuous because it has asymptotes where it's undefined. But at every point on x, not at one of those asymptotes, it is a continuous function. There is I don't want to say continuous because it's not. It's broken into pieces. But it is a function that is defined at every point of x, not one of the asymptotes. So, and it does repeat. I mean, you can look at the picture, and even though it doesn't look like a nice, pretty wave, you can still look at it and see it does repeat. It's not a pretty picture, but it is still a picture. And just like I asked about the tangent and cotangent function, how long does it take to get from one value of 1 to the next time it equals 1? From -2 pi to 0. From 0 to 2 pi. So the period of secant is 2 pi. And for the same reasons, the period of cosecant is 2 pi. And that was truly an astounding observation. You need that really was good. It's the reciprocal of a function that has a period of 2 pi. It only makes sense that it has to have a period of 2 pi. Well, we did it to sine and to cosine. What happens when we change the amplitude of a tangent function? It's going to stretch it. This point here where it equals 1 is going to move up here where it equals 2. What's going to happen where it's equal to 0? It's 2 times 0 is still 0. The amplitude doesn't changes that, and the board's not tall enough, and neither am I, to be able to draw it with a nice pretty curve so you can see what it looks like. Hopefully there are pictures in the book that'll give it meaning. You change the amplitude, you stretch it vertically. Any of you old enough to have played with Stretch Armstrong? No? You don't ask? Okay. Yeah, I know. The rest of you are going, stretch who? What? How about silly putty? Anybody ever play with silly putty? Pick up a... Does anyone... If I talk about the funny pages, are you all going to look at me like I'm stupid? The Sunday paper, you remember a paper? It's like a web page, but it's manual. They had the colored funny pages every Sunday. You take your silly putty and press it, and you pick up and get the picture on the page on your silly putty, and then you could... Okay, I can't, but someone hit him. Yeah, you could stretch those pictures and make them look all kind of silly. Well, that's what changing the amplitude of tangent does. Is it the function stays within the asymptotes, but it just stretches taller and taller. Now, you know what? If this was a physics class, I would. So y'all all think that I'm stupid because I went into physics, but all that means is when you do it, you're just playing. When I do it, it's research. Okay, what do we understand what the amplitude does to the tangent function. Now it's time to put a Charlie horse in your brain. What happens when we change omega of tangent? Where omega is no longer 1. Little point of order business. Has anyone not signed the sign-in sheet? Here you go. You and him and anyone else that hasn't. That's exactly what it does. It changes the period. That's exactly what it does. The period, and this is a Greek letter tau, by the way, not a capital T. It's the uppercase tau, but not that it matters on your typewriter. Or is a typewriter something that nobody... Y'all have all seen typewriters, right? Okay. Yeah. When I started undergraduate school, I actually started with a drafting table, because in electronics, having to do schematics, and I started with a drafting table and an electric typewriter with daisy wheels. That I had to buy separate daisy wheels for the Greek letters and for all the math symbols. And you want to talk about, you do desktop publishing. It was quite an ordeal when I started undergraduate school. Okay, what happens to the period of What's the period of that? The period of sine omega x is the period of sine x divided by omega. Who wants to guess what the period of tangent omega x would be? Say again? No. Good guess, but no. What's the period of tangent? No, the period of tangent is pi. Pi over omega. So when you change the amplitude, you stretch it vertically. You don't add, the amplitude is already plus and minus infinity. So it's not like you can make it any taller. What you can do is stretch it out in that same period, in that same range. And you change the period to pi divided by omega. Now we're not going to try and draw that because this is already messy enough. But you should be able to imagine how you would find your new period, mark off your asymptotes, mark your key points. Where is it going to be 0? Where is it going to be 1? And then stick in your graph. What? The cotangent? Yeah, it never... Well, no, tangent at exactly minus 2 pi, tangent is exactly 0. And it crosses at that point. It's the cotangent that will be undefined at minus 2 pi, or at any multiple of pi. And it will be infinitely positive to the right and infinitely negative to the left. And that's at every pi, every multiple of pi. Okay, well, we did it to the... I assume that you can see that it would be the same thing if we were doing cotangent. The amplitude would stretch it. And omega would change the period. The angular frequency or angular velocity would change the periods. So it would become, again, what's the period of cotangent? Pi. So the period of cotangent omega x would be pi over omega. All right, well, what does that do? It moves these peaks up or down. It spreads the distance between the functions, where they, it expands that exclusionary range, that range of exclusion. Okay? That's the same for secant and for cosecant. And what does secant omega x, what does that change? Again, it changes the period. What's the period of secant? 2 pi. So the period of secant omega x, 2 pi over omega. Do we have any questions? Are the pictures helping you to sort all this out in your head? Finally starting to make some sense. Do not forget this. I'm going to repeat this. I'm going to come back and I'm going to touch on this one more time, repeat it, just because hopefully repetition will make you remember it. Do not trust your calculators. They are not a replacement for your brain. All computers are blithering idiots. You've heard the expression garbage in, garbage out. This is true of every computer. It is a blithering idiot. The only thing it can do is count from 0 to 1. It can just count from 0 to 1 about a bajillion times a second. Okay, so it can calculate an algorithm and give you a number out to more decimal places than are meaningful in the time it takes you to push a few buttons. But it does not replace your brain. You have to know what it's going to give you and how that applies to what you're doing. If you forget to change it from degrees to radians, or if you forget to change it back, it will give you a wrong answer. And when you punch in a value of tangent and ask for the, and then ask for the inverse tangent, it's only going to give you something in this bandwidth, in this little band right here. If you're working outside of that one band, it's up to you and your big brain to figure out which one of that infinite number of x values you're actually looking for. All right, well, I guess we're close enough to the end that you're all getting restless, so I'm going to shut up and y'all can go home. Anybody has homework to turn in, set it on the pile.